see, so the key discriminant it's going to turn out that tells you about the particulars of the nature of dark matter, or aggregates, remember, is the amount of surviving clumpiness is a strong function of the nature of the assumed particle, on how collisional it is, whether it's completely collisionless. So cold dark matter, I should mention, is collisionless. So if two cold dark matter particles collide with each other, they go through each other, they go past each other. Okay? They don't actually rebound and create pressure like you have. So gas in this room, right? So there's air in this room, there are these gas molecules, and there's pressure in this room because the gas is colliding against the walls, right? So there are these unbalanced forces at the wall, so that gives you the pressure in this room. The cold dark matter particles in this room have no pressure. Cold dark matter particles have no pressure because they don't collide. Okay, so the equation of state, so we actually describe dark matter by how its pressure is related to its density. So this is a very, very common way of characterizing the physical properties. And for cold dark matter, it's P equals 0. Pressure is 0. And as you may know, for gases, it's P equals 1/3 rho, and so on and so forth. Boyle's law, etc., come out of that. Right? So it turns out that you can constrain whether dark matter has fluid-like properties or is collisionless by looking at the surviving number of clumps. Okay, let me quickly punch out here. How are we doing on time? Are we really going on? Or?
It's been about 50 minutes.
Okay, great. I think I'll be.
Another short question on the simulation.
Yeah.
The movie is clearly two-dimensional, but the physics is three-dimensional?
Yeah, fully three-dimensional.
It's all three-dimensional.
Fully
So
three-dimensional.
you're just projecting on it.
Yeah, we're taking projections, and we actually build up statistics by doing projections along different axes.
But you have a huge number of degree of freedom. I really. So there are no collisions,
No.
if I understood correctly. This is the model, there are no collisions.
No. But the thing is, we actually do have three-dimensional information as well, because we know the locations of galaxies spatially, x, y, and we also know their distance from us in these redshift surveys. So we do have 3D information with the data as well, which we can compare.
I have a question as well. This is something that is not collision. Is that just a simplifying assumption, or is it not?
Oh, no. It's not a simplifying assumption as such. It appears that that is the equation of state that is compatible with the power spectrum that we measure. I think it's well supported, I would say, at this point. It's well supported by observational data. It could well turn out that not the entire inventory of dark matter is these particles. And that dark matter is a combination of some particles that actually do collide, some things, or maybe black holes, remnant black holes, as well as this exotic stuff. That is still an open question. However, okay, so this is what the model predicts. So the model predicts this relative fluctuation amplitude, the power spectrum, as a function of scale. So perversely, this is increasing scale, and that is small scales. So these curves are what the model predicts, okay? And these curves are what you can calculate from the simulations, because what goes into the simulation is an initial condition for this curve. And then the simulation propagates it in time with all the dynamics of gravity, and it gives you an output today, okay, of what this power spectrum should look like, what the transformed power spectrum today should look like, because you started out with some initial condition. And what we want to do, ideally, is we want to plot data on top of that. Right? And as I said, the data is, of course, galaxies. The prediction is dark matter. So modulo our formation of paradigms that we have for the formation of galaxies, the hope is to put boxes here and constrain these models. And just to show you the discriminatory power that these models have, these two lines, the black and the red, which it turns out the data cannot discriminate at the moment, are two models, one in which neutrinos, not neutralinos, but neutrinos, these other particles in the early universe, with a small mass can constitute some of the dark matter. Okay, so the discrimination comes, it's tiny, we can't quite discriminate in the power spectrum. As I'll show you, there's a different set of observations that will help you discriminate it slightly better. But this is the kind of discrimination that we can do between models. So what has been ruled out at the moment is that this dark matter is made entirely of neutrinos. That's been ruled out. It could be that a small fraction of neutrinos still contribute to the dark matter budget, but the bulk of dark matter needs to be collisionless and cold. Okay? And I'll show you these are projections for surveys and so on. I'll show you the real data in a minute, and I want to show the real data to you. I want you to look at this shape, right? And I want to show you the real data without the theory plot. And it's overwhelmingly supportive of a cold dark matter. So anyway, these are all the various probes. So these are the various observational handles that we have. Remember, this anchors everything. This anchors the initial conditions we start out with in our simulations. Then we have statistics of gas blobs in the universe, supernovae properties. We have some constraints on the amount of overall hydrogen in the universe and helium in the universe that we understand extremely well. And then there are galaxy surveys. There are surveys of ionized hydrogen that we have a reasonably good inventory of. And then we have these galaxy clusters. We have gravitational lensing. So we have a whole range of probes. And this is just a picture. This is a very nice slide from one of my colleagues, Max Tegmark. This is just a nice animation showing, you turn the crank on these simulations, and what you come up with, what you come up with is, it's surprising we come up with so much, given that you don't know nature of dark matter, you don't know nature of dark energy, but you still come up, so this is what you come up with. And this is the power spectrum. So this is the prediction of the cold dark matter theory. It's a curve that goes exactly through these observations. Okay, I haven't put that in because I don't want to distract it. So these are the observations. These are real observations with error bars. Okay, with that, and I think fairly careful error bars. So nothing is sort of wildly crazy here. The observations, there may be some underestimates, there may be some systematics we don't know, but by and large, this is extremely well constrained by the cosmic microwave background. This is the largest scales. This is the smallest scales. And progressively, when we start going down the slope here, is when the particular relationship between mass and light starts to matter. Starts to matter more and more to determine this slope. But it turns out, and these are all different kinds of objects, because these are globally averaged over classes of objects, we can't parse out mass and light relationship as a function of scale just from this plot. But by and large, there's an excellent match. And that this is the plot that makes people say that the standard paradigm works. Okay? And that lambda CDM is the theory. Okay? But as I've showed you, right?
What does lambda mean in lambda CDM?
Lambda is a cosmological constant. So it's a dark energy. So the current estimates of dark energy are synonymous with Einstein's cosmological constant. We don't have any, we don't have data at the moment. It looks like this dark energy is a constant. Potentially it could vary with time. And we don't, I think in the next 10 years we may have some idea of if it varies with time. And if it varies with time, then Sean's idea of the future of the universe could look different. His assumption is that it's a constant dark energy and there will be a progressive dilution, right, as time goes on. That might change in 10 years' time if it turns out that there is some cyclical acceleration, deceleration in the universe, and we see some evidence for it. We haven't seen any evidence for it yet, but we also don't have the experiments that would have the sensitivity to do so yet. But in the next 10 to 15 years, we may.
Can you go back to what you said before?
Yeah.
Why is clear that you exclude neutrinos? You said something that is completely clear that
They cannot be the only contributor.
and this is seen from one of your pictures.
No, this is seen from the slope here, from the Lyman alpha.
I see.
Remember, if you notice that the differences, I can go back to that slide. The differences between a massive neutrino contributing and not contributing really start to show up here.
I see.
And so that is where you have that part of the fluctuation spectrum is where you have the sensitivity. And the constraint I was telling you comes from the fact that these error bars are really quite tiny.
Okay.
Very powerful here. It's a bit ropey here, but it's very powerful here. Okay, so quickly let me move on to talking a little bit about my work, and I'll try to go through this quickly. But one of the reasons I want to do not so much self-propaganda, but propaganda for this method, because I think this is one of the cleanest methods because you circumvent any assumptions between, or the relation between light and matter.